And the answer is, maybe you can trust them if they're your friend, but not if your friend attracts attention, right? Because if your friend attracts attention, then you end up in a situation where you can just monitor that one point. You just need to watch either side, and if there's no encryption, you get everything. You get to see who's talking to who, and you get to see what they're saying. So what we did with TOR is we created a system where we abstract some of these risks away, and we separate them. We say, we want to have multiple hops. So relay 1 knows about Alice. They know where Alice is coming from. So they know Alice is in Jordan. Relay 2 only knows about 1 and 3. 3 knows about Bob. Bob could be Amazon.com, it could be Twitter, or something like this. If you can get to relay 1 safely, your link is encrypted between Alice and relay 1. And between relay 1 and 2 and 3, all the way until you leave, unless you use another protocol. If you use SSH, for example, then it's encrypted through the entire network. So for example, the first link can totally say that it's you, but they don't know who you are talking to, so they don't know you're trying to talk to Bob. They, for example, might try to influence you, but TOR takes steps to stop you from going to a particular site, to stop you from doing things that will influence your destination. So that's something that's quite useful. Yeah?
So you said just that R1 doesn't know that who we're talking to.
That's correct.
How can Travis?
Well, we'll get to that in just, let's see, one more slide after this. So the question was, how do you do this? And the answer is cryptography, right? And I'll show you with a nice little diagram on the very next slide, I believe, what that cryptography looks like at a high level. So a last hop, for example, you're in the TOR network at this point. And if you're in the TOR network, that's a good sign, right? It means that you can get, probably, if this server allows you to talk to, say, any website you want to visit, like Al Jazeera Talk. I think that's my favorite example from this trip so far. But you could, if it allows you to go to it, then Al Jazeera Talk, they will see that you're coming from R3, right? So this is just like a proxy. You know, your IP address changes, but it's a little bit better. Because the corrupt hop, if this guy was a bad guy, which let's just assume that there are a lot of these bad guys in the world. If they're a bad guy, they only know that someone or something, like a script or some sort of machine, is talking to Bob. But they don't know that you're in Jordan, and they don't know that your name is whatever your name is, right? So you get this like nice level of abstraction. And if you have, for example, some sort of authenticity, if you have some sort of identity that is verified in some way, like let's say you use SSL, it's not perfect by any means, but it's a little bit better than nothing. And if you have that, then potentially relay 3 can only see that that machine is talking to another machine, but they can't even see what you're saying, because you will have confidentiality from other layers of the network itself, and from SSL, for example, when it's on top of the TOR network. So this is how this works. Can you all see the green and the yellow and the blue? And then inside you have this like white line. So the basic idea is that Alice takes a message, and if you've seen our logo, it's this onion logo, right? And the idea is, we don't actually use real onions, obviously, but the idea is a lot like an onion. You have a message and you encapsulate it, and you encapsulate that message again, and then you encapsulate that message as well. And what you end up with is that you encrypt, you create a session key with each of these systems. And you basically create tunnels. So you can send this data back. And each one knows that when data comes in on a particular circuit, on a particular stream, it has rules for how to forward them. So each one has a small partition of knowledge about you. And all 3 of them have to collaborate. Or someone has to watch the first and the third. So in theory, you could just get those 2. And there are some attacks where they try to just get those 2 by doing a timing attack, like delaying a packet here, and then looking for the delay here, and then saying, oh, this delay happened here, therefore this relay here is over there. You know, it's talking to that user. So there are some attacks that are like that. But in general, the idea here is that with 3 hops, you abstract out enough of this risk that 1 knows just a small amount, 2 knows just a small amount, and 3 knows just a small amount. And we think that that is pretty good. And there are some designs where, for example, 4 hops might be better because of some issues with congestion. If, for example, if an attacker is trying to like fill up the load of all of these machines, Christian Gruthoff, the author of GNU-net, did a congestion attack on the TOR network, which was pretty effective. The idea was that he controlled R3, but he didn't control anything else in the network. And what he did is he saw you trying to go to a particular website, and what he did is he said, for every server that is a guard node, someone that is allowing entry into the network that a user chooses, we're going to induce an incredible amount of stress on those servers by sending lots of messages they have to process. And we'll do it in a binary search way. I think it was a binary search that he did it with. And basically the idea is that he induced the load in a way where he could see that this was loaded. The way that it worked is that he put an iframe with a meta refresh tag in it, so it got around JavaScript filters, and it would cause a consistent reload. So it doesn't matter how long it takes the message to get through the network, it would cause a consistent reload. And so when he would induce load on R1, he could tell who your first hop was to a relatively good degree of certainty. So that's a pretty scary attack, and it's a problem, for sure. And we are working on fixing that, and in fact we have started implementing things that are countermeasures to that. But at the end of the day, he was able to control you being on his server. He couldn't guarantee you would be at that server at one point in time, but if you ever hit it, and you ever used an unencrypted HTTP protocol, then he could use that to automatically induce load on the network to try to figure out which TOR server to monitor, for example. And that's effective, but not so effective now because some of the countermeasures that we've implemented. But ultimately, at the end of the day, it's still the user was not de-anonymized, right? You didn't know who Alice was, but you had a pretty good probability of guessing who Alice talked to first in the network. And that was a scary attack. And so we have to think about this, right? Every security vulnerability, every like bug, every just like silly thing becomes an anonymity attack of really grave proportion, right? It becomes very serious very quickly. Because if you have an exploitable bug, generally, okay, so you can compromise a machine, right? Well, if you have an exploitable bug and it's in every machine in the network, well, that is a really big problem for someone that relies on the network for anonymity. So to give you an idea about how the network is actually structured, you have these servers. Let's say, does anybody here have an internet connection at home that's unmetered? Just like a DSL line or something like this? Okay, I expect all of you to go home and set up TOR servers. Thank you. Okay, so here's how it would work if you did. You decide that you care about free speech, you care about anonymity, you care about having access to information, or you care about the world being able to see the internet from Jordan's perspective. So you can share your internet connection out. And the way you do it is you start the TOR software, and you're S1, you're the server. You publish your information. You publish what's called a descriptor. And it includes things like your IP address, the port number that's reachable for your onion routing port, that's where you send encrypted data, or your directory port if you want to mirror the list of all the TOR servers. And you publish this information along with some cryptographic keys, and you send it to the trusted directory. There are 7 right now in the world. They vote based on a consensus. And the way that it works, I run one of these servers, and everyone publishes to me, and they publish to some other people's directory servers. And we all look at the things that are published, and we probe them, we check them, we see how much bandwidth they offer versus how much bandwidth they actually have. We do some corrections on the network, but basically what we do is we take a snapshot. And we say, these 1,500 servers, they are what we're going to call the TOR network. Each server signs this consensus, and it gets pushed out to different TOR servers that are running the directory mirror port, or also to the trusted directories. They obviously have a copy since they made it in the first place. They push it out, and then a user starts TOR and downloads a copy of that list. They check the signature, which is verifiable because the TOR binary they have solves the key exchange problem, right? You know that when I sign a consensus, my cryptographic key